Dion is a senior fisheries biologist from the Ministry of Fisheries, and he works in the phytoplankton section, which he heads, and he's been working there since 1994. He has an MSc in coastal oceanography, as well as a PhD in marine microbiology from Rostock. So his research interests lie in phytoplankton dynamics, as well as looking at the seasonal and interannual variability within phytoplankton species, how this relates to determining if you can get a signal from that and relate it to the commercial fish stocks.
Thank you for the introduction, Chibo, and good afternoon, everybody. As Chibo said, title of my presentation is Dynamics of Phytoplankton in the Benguela Upwelling System. I will present mostly in situ data which will be presented has importance because I'm working for Ministry of Fisheries. Most of the work we do at Fisheries tends to go in supporting the resources group. So keywords will be related to this presentation is harmful algal blooms, species, Benguela upwelling system, and remote sensing. In the introduction, I will refer to publications in which you can find most of the information, such as objectives and hypotheses and some of the most important challenges in the system, and will give a general information about the Northern Benguela upwelling system. The methodological part will cover the area, sampling, analysis, and I will focus specifically on chlorophyll A in species and the availability of survey data that we have. In the results, I will show how the ecosystem behaves in terms of the driving forces, and in this case, it will be wind, temperature, and nutrients. I will also focus on the phytoplankton climatology and the mechanisms of the blooms, functional group, trends, and I will look at diatoms and dinoflagellates, and then we'll focus on species, or some of the main species that we have on the Namibian shelf. So for my PhD studies, it was related to this topic, high phytoplankton blooms in the Northern Benguela upwelling system, with special emphasis on chlorophyll A and the toxin-producing Pseudonychia species. 4 papers were published, and the basic concepts were space-time patterns of phytoplankton blooms and its relationship with physical forcing, space-time patterns of Pseudonychia blooms and their relationship with the general phytoplankton assembly and physical forcing, morphology and toxicity of Pseudonychia species during bloom formations and potential harmful effects in the NBUS, and description of new Pseudonychia species and exploring potential toxin production for the identified Pseudonychia species. Just a brief overview of the NBUS, and you've seen this quite a few times now. The Benguela is one of the 4 major eastern boundary upwelling systems, consists of the NBUS and the SBUS. It has sustained a large fish population in the past, and fisheries is still one of the major GDP sources for Namibia. I think it's the 3rd. It is wind-driven and highly productive upwelling region, which can be seen on this modus chlorophyll image, which shows the high productivity along the Namibian coast. As shown in this image, the west Benguela upwelling system is very dynamic and complex. However, only the main features of the system are captured, which is the Angola current, which is across the north central Angolan shelf, the Angolan Benguela front, which is approximately there, the north and central Namibian shelf, the Luderitz Orange River cone, which is somewhere, Orange River cone area, which is somewhere there, and then the Namakwa shelf around there. However, the region of interest is, of course, this carbon-rich and oxygen-poor area, the coal productive upwelling system, and the currents, which is equatorwards flowing. The upwelling is a very complex process, but this upwelling animation shows it in a simple way. This has been shown by many speakers already, and I will not elaborate more except to say that one of the main driving mechanisms behind the upwelling is, of course, the wind. In our case in Namibia is the southerly winds. An even more simplified way to look at the NBUS from a habitat point of view is there's an upwelling period and then a non-upwelling period. But we also have this intermediate or transition zone period between these two main events, if I can call it, or periods, if I can call it like that. As I'm working with phytoplankton as food in the system, in the water column, my interest is focused on the behavior on an annually and on a seasonally basis, focusing on community structure, functional group, species, size, chlorophyll maximum, and sometimes toxin level. During my studies, or the hypotheses were actually related to this chlorophyll Hofmuller plot, which is used to show food availability for fish on the Namibian shelf. So this Hofmuller plot shows the behavior of phytoplankton in the form of chlorophyll A using remote sensing data. In the Lüderitz upwelling area, it shows low abundance, and one of the reasons is the turbidity of this area. The central area shows high phytoplankton blooms and not so clear seasonality. And then the northern part shows high phytoplankton abundance without, while the northern part shows clear seasonality, as you can see with these phytoplankton blooms in between. Therefore, the established hypotheses were that there is seasonality in phytoplankton blooms driven by particular forcing mechanisms. The blooms may have harmful consequences for the ecosystem, and that Pseudonychia species can cause toxic blooms in the northern Benguela upwelling system. About challenges, by explaining the complexity of the system and the importance of fisheries for Namibia, it is important to emphasize the main challenges that we have in the area, which has important influence on the choice of topic I had. So sulfur eruptions coupled with low oxygen and dead animal wash on the beaches, harmful algal blooms in terms of high biomass or toxicity together with dead animals found on the beaches, as they pose a serious health risk for the local population, and sometimes unknown events on the mariculture farm still remain unexplained. So a brief moment just to show how we do our sampling or the program that we have. Although NatMurk has set up a monitoring program along the Namibian coastline, I will focus the 23 line, and more specifically at the 10 nautical mile station. This is the longest time series available and historically fishing grounds on the shelf. I've extracted data from a long phytoplankton time series since 2000, together with other parameters. We have measured during surveys done in Namibia to describe the different forcing and phytoplankton communities. So how do we do it? We normally go out with our research vessel, or in the past, the Welwitschia, and using Niskin bottles to collect sample for measurement of chlorophyll A, which was filtered on board using GFF filter papers, and additionally another bottle for species which were by adding Lugol's to the sample bottles for identification later on. The filters were brought to the institute where we extract chlorophyll in acetone overnight at a -20 freezer, and then analyzing is done with the fluorometer, which is regularly internally calibrated to assure the quality of the results. Species were counted and identified under inverted microscope using the Uthermal method. Here, most of the surveys are listed. All obtained data is kept in an established database. Unfortunately, due to challenges beyond NUTMERG or our institute, as you can see, samples were not taken that regular, which is the limitation in answering some fundamental questions about the northern Benguela upwelling system. As I already mentioned, I've used physical and chemical parameters such as wind, temperature, and nutrients to explain some of the characteristics of the NBUS ecosystem. So for the purpose of this study, a 12 to 14 year wind time series were extracted to calculate the climatology of the wind. Although the variability of wind was huge, two major wind peaks were observed, one in March, April, around here, and a second one in August, November. And as you can see, the August-November peak was higher than the annual median. So although a longer time series exists for temperature on the 23 line, only data from 2000, around 2000 to 2012, was extracted from the database. So this image shows the variability of temperature from inshore to offshore, which is around 70 nautical miles, and the black dot shows the sampling points. Seasonality can be noticed. Colder water presenting upwelling and can be noticed mostly inshore, and warm water predominantly offshore. When you are analyzing this 10 nautical mile station inshore, seasonality becomes more evident in the water column, which is from surface to around 100 meters. During the same period, of course, this time series show very important feature, the thermocline, which is approximately between 15 and 20 meters. Cold water intensity during upwelling periods and warm water intrusion, example, as I showed here, from the north, that's the warm water, from the northern part of Namibia, and sometimes reach the central part, and which we sometimes then call the Benguela Nino, such as in the case in 2011. So calculating the climatology seasonally is not debatable, with the highest temperature found in March, as you can see from the surface plot, and also the highest variability during March, and then the coldest period during September, August, September, or October. Three temperature ranges becomes really important from my point of view. It's the 13-degree isotherm, which seems to be the threshold for upwelling, and then temperature between 13 or 14 and 16 degrees, which I called intermediate temperature, and which is a weak thermocline, and then around 16 and above, which shows a high thermocline, or yeah, not a high thermocline, but yeah, intensity. So looking at the nutrients, during upwelling, nutrients will be suspended in the water column, of course. Nutrients are critical for phytoplankton growth together with sunlight. On the slide, the behavior of nitrate, phosphate, and silicate shown with emphasis. This is for the 10 nautical mile station. During upwelling period, which is August to November, it was obvious that there were no shortage of nutrients in the water column for these nutrients. However, from the beginning of summer, which is around December, the upper water column close to the surface becomes severely depleted, and concentrations even falls below the low-term average, as you can see in these three images. So I'll focus now on the phytoplankton or the trends of phytoplankton using chlorophyll A as a proxy for their abundance, and calculating the median chlorophyll A from inshore, which is the 2 nautical miles to the 7 nautical miles. One can see the high variability, and however, if you look at this, you can see the highest biomass is found more or less inshore. The intermediate or transition zone around 40 and 30 nautical miles, and a low biomass which is offshore. So the following animation, which I'm going to show the parameters I have discussed and what influence it has on phytoplankton blooms in the northern or in the bus. So, sorry. The wind, let me see if it comes up. Okay. The wind, which I've described previously, shows the 2 wind peaks as seen in this graph. The effect can be seen in the water column, showing the cold, nutrient-rich water after upwelling and during the non-upwelling period. Nutrients, of course, are in excess in the water column, and a weak thermocline and a strong thermocline develop during the non-upwelling period. So 3 phytoplankton blooms can develop annually, as you can see on now. A primary bloom, which is just after the upwelling period, and which is sometimes called the spring bloom. A weak thermocline, which has developed, which helps to stabilize the upper water column due to lack of wind, as you can see here. This bloom is closer to the surface as well. However, quickly, except for this part where we normally don't sample in January, is used up by the nutrients, because the nutrients are trapped under the thermocline, and a decline of phytoplankton can be experienced due to lack of nutrients in the upper water column. However, a secondary bloom can then develop by the end of March, April, as wind breaks down the thermocline and mix the nutrients into the upper water column, providing food for phytoplankton. Then a third bloom is possible, which is subsurface, which might develop around July to August. And this might be due to what we experience now, east weather conditions or bergwind conditions, which helps to stabilize the upper water column. And due to a brief relaxation of our southwesterly winds, this third bloom might become possible. So I'll shift the talk now to phytoplankton species. So calculating the phytoplankton climatology for the past 20 years for the 10 nautical mile station, combining all the relevant phytoplankton groups or species, diatoms, dinoflagellates, flagellates, and coccolithophores, the following trend could be noticed: 2 phytoplankton peaks, the lower abundant primary peak in November, December, and the higher phytoplankton peak in March, April. However, the following graph from a statistical point of view, in taking the high variability in consideration, the primary peak might be the highest. Although this is still under investigation and ongoing. Okay. Focusing just on diatoms and dinoflagellates. On the 10 nautical mile station, the following can be noticed. There is no long-term trend for diatoms or dinoflagellates. Diatoms dominated, and dinoflagellates seems to be less than 10% of the total abundance, except in 2018. Showing the climatology, the dinoflagellates increased during February and March, but still remains quite low, or lower than the diatoms. And then the third climatology graph, which shows the abundance of diatoms on the x-axis, you can see here in the green. A diatom peak can be seen in April and in December. Or then a dinoflagellate peak is around March to April. And also just quickly, just to show that if you look at the values here, the diatoms is of course much higher than the dinoflagellates. What is also important to notice is that during the upwelling period, that phytoplankton or these diatoms and dinoflagellates is actually very low, and also in the middle of the non-upwelling period. So overlaying the diatom species, which are the main contributors to the biomass on top of the chlorophyll blooms, it can be noticed that the blooms might become species specific. It seems from this preliminary data analysis that Chaetoceros and Sclerotonema might contribute to the primary bloom, although Chaetoceros is found more or less throughout the year, whereas this Thalassiosira species and another group, Leptocylindra species, might contribute towards the secondary bloom, which is in April and May, or May on this period. However, a third bloom shows, which is not shown in terms of the chlorophyll, seems to become more it appears, and this group is very important in terms of this is one of the only diatom species which is producing toxins and can pose a health risk with negative influence in the upper food chain as well. So this graph shows Pseudonychia blooms along the 23 transect from 2001 to 2014. It was clear that Pseudonychias occur from inshore to offshore. Using the European threshold for possible blooms with counts of around 200 cells per liter, it was visible that Pseudonychia blooms were regularly occurring off Walvis Bay on the 23 line. Two extreme blooms were standing out, 2005 and 2011. And in the meantime, these blooms were explained in the publications. However, this graph was in the meantime extended, and a third major bloom can be noticed in 2016. So I used the 10 nautical mile station again, and when calculated the climatology again for Pseudonychias over the 14 years, it was noticed that the blooms of Pseudonychia might occur during April, May, June, and July, and that they were less possible during the upwelling period. And recalling the climatology of wind data, which I already presented, the important features of scenarios become noticeable. The likelihood of Pseudonychia blooms occur after the main high chlorophyll A phytoplankton species. In the manuscript, I just described that there are no correlation between chlorophyll and Pseudonychia. And Pseudonychia blooms occur during the period when the wind slacks after the first peak. However, the second wind controls the Pseudonychia bloom. In other words, the bloom are broken up. So briefly about future work. This graph shows preliminary climatology chlorophyll A trends in different regions along the Namibian coast. And using remote data, this might lead towards maps of food abundance and possible fish feeding behavior. And linkages still need to be explored, of course. Maps might become possible for phytoplankton size and functional groups might also be possible. And using historical data from the in situ data that we collected, ground truthing for specific species might become possible. Example, in the case of Pseudonychia, which is important from a managerial point of view. However, Christo, the next speaker, will elaborate more on these topics, and it can even become, I think, more for even for specific areas, which might be possible. And thank you for your attention.
So, if there are anybody in the audience that would like to ask Dion a question, then you can please go ahead and do so.
Dion, Anya here. I might have missed it. Your climatology of the temperature in one of the first slides on the 10 nautical mile station. At what depths? What depths did you select there?
For the temperature, the first slide is the surface slide, which is up to around 15 meters because we use in situ data. And then the second climatology slide is up to 100. It's also for the 10 nautical miles station.
But if you say up to 100, how did you take the average then, or what?
No, if you look at it's not the average. Okay, now I can't
because
get
you've
to
got
this.
Distance on the y-axis from shore, and you've got time on the x.
Let me quickly go to the slide again. So this is on. You're talking about this one?
Yeah.
Or you're talking about this one?
I'm talking about the one, the Hofmüller plot, that one, yeah.
Yeah. No, this is it was an average which was taken at about 15 meters approximately depth.
So it was taken 15 meters depth. Okay.
Yes.
That was all I wanted to know.
Oh, okay. Just to exclude the solar radiation that you normally have and that can influence the, okay.
Okay, thank you. Can you switch off your mics? And then any other questions from the audience? Good.
Yeah, thank you, Chris. My question would refer to slide number 29. Okay, in particular about the 218 dinoflagellate bloom.
29, this one.
Yes. There you have a huge bloom of dinoflagellates in 2018. Were those toxic? And my second part of the question is, what can you say about toxicity development from all your data?
Okay, 2018, no, it was not toxic. It's still under investigation, but there was no toxic species for that group or during 2018, or rather the abundance of the toxic species was very, very, very low. And about the toxicity from the Pseudonychia species, I managed to find out that there is quite a bit of different, there's toxic species, but those species might be toxic or not toxic because of the different strains you might get. And what was interesting was that, for example, the 2011 event for the Benguela Nino, when there was, it seems, a phytoplankton species change or shift in phytoplankton species, and also for the Sidonichias, that the one group which was toxic just changed to another group which was also toxic, although they were still Sidonichias.
That's what I would expect almost, but what makes them produce toxic? Can you relate that to some kind of climatology event, or what was it, or is it?
Actually, there is research and there is many factors that might do that. It can be nutrients, can be even a behavior. If they are starting to feed on the Sidonichias, so they don't have a clear answer why Sidonichias become suddenly toxic. And as I said, I think many people are doing research with not a clear answer to that. And even in Namibia, we actually do not do toxicity, because I normally send the samples to another country where they test for that.
Okay, thank you, Kurt. I believe you're happy with the question. Are there any other questions? I see we are already quite a few minutes past the half hour. So if there are no more questions, maybe then we can go to the next presentation. Chibu, would you introduce Christian?